solutions that need longer time. In a sense, in a time scale, it could be 10 years or so. And likewise, some of these examples you will see they are really in terms of dimensional scale. I'll talk about some nanowires, nanoscale devices also, and then leading up to macro scale or large area, as our skin is distributed over entire body. So to me, that becomes a large area. If time permits, I'll move to the third section of my presentation, where some of these technologies can be used in context with humans, and that will close the loop of what I was saying earlier. Some examples we have used, how we have used these technology, electronic skin technology, to improve our own lives through development of various sensor patches, etc. And then I'll conclude. Okay, so why do we need electronic skin? This example is good enough to highlight the importance of electronic skin right from the beginning of a human life or any animal life. So a child growing in a womb, if you see, there is no possibility of vision or audio. Only possibility interaction is via touch. And that highlights the early stage of development of a human body or any animal, where touch plays an important role. And so it comes much earlier than other sensory modalities, and then processing in the brain also starts much earlier. Another example in real life could be, if you look at this example here, if you try to grasp, put your hand on an ice block and try to grasp an object nearby, very likely you will fail. Object will slip out of your hand, and you can see that it's happening, but there is nothing much you can do about it, because you have lost momentarily, you have lost your touch sensory feelings. And that highlights the importance of touch sensing and raises an important question: why are we developing prosthetics without sense of touch? Many examples given in previous presentation, there were exoskeletons without any tactile feedback, or let's say little tactile feedback. So this also then goes to automation. If you look at this slide, there are some robots working in cages. Literally, if you can see, there is no human in these cages. And this is the current state of the art. If you go to any car manufacturing plant or any automation sector related factory, and if by chance a human enters into this space, this is what you come across. You come across news such as robot kills man at Volkswagen plant, or man dies in electric shock from robot. That was an example from Gurgaon in India. And a long back example from Japan is at the bottom right. So the important question this raises: why are we developing machines which actually end up killing humans? A skilled worker should, even if the skilled worker enters into the workspace of a robot by mistake or by accident, robots should not be able to harm. Robots should be equipped with sensors so that robot stops and human is not harmed. So machine is for us, we are not for machine, and therefore machine should not cause any harm. We should develop in such a way. And this also highlights the importance of touch sensing. And when I say the electronic, I will use this electronic skin, tactile skin, touch sensing. These terms I'll use, and synthetic skin. So various slides, but they all, to me, they all mean same. So these are also important because you want safety of humans, and particularly because robotics is evolving so fast towards Industry 4. I'm not sure if you have heard about this concept of Industry 4, but it means that robots in future, in a industry, in a automation sector or various other sectors, we expect humans and robots to be working side by side as two humans do today. And if that is to take place, then physical interaction via touch is extremely important. Safety is extremely important. So This is another example where in the industry example where touch sensing or electronic skin will be important. There are few more examples given here in this slide. On the left hand side, you see some examples where tactile skin or electronic skin is needed today. These examples are taken from medical sector. As you can see, this is a Da Vinci robot. Current state of the art is that there is no haptic feedback coming from the patient side. Doctor sits here, they see in a console, and they using a probe, they move the robotic arms around, and they carry out precision, uh, quite accurate operations or surgeries, but still it's not accurate. So I said quite accurate. And tactile feedback from this end will be very helpful. And for that, you need to cover these robots or these at the end effectors with ultra thin uh, electronic skin that can give a sense of pressure applied or palpation, etc. Likewise, example of this laparoscopy example that you see here, current state of the art or minimal invasive surgery in general. Current state of the art is that you have a keyhole which is about, let's say, 5 millimeter diameter. You insert the instrument inside the body. Then you insert another instrument which is just a camera to see what is going on. Now you are inside the body. It's like a black hole. You are trying to actually uh, see something which is it's quite difficult. And other thing is that there's a camera over here. You are trying to manipulate the soft tissue, soft or hard tissue, depending on what you are seeing. So you are trying to feel it by seeing. That does not connect very well. We know that there are visual illusions. So it may not be a highly accurate surgery. And in that context, if this surgical tool was covered with electronic skin, you may see a pressure map from inside the body, and using pressure map you could build what is inside the body. You can feel whether the tissue is hard or soft, etc. Going forward, if you look in future, these are some of the on the right hand side are some example which are pulling this research. These are the pull factors for future, whether that's a retail sector that you are these days. It makes a lot more sense because we are not physically going to shops there. Everything is online these days. So you purchase clothes online, but you cannot feel whether what is the texture of those clothes. And and if you as a 3D, you cannot really see that. So touch sensing or haptics is so important in that area, or in context with, let's say, again in today's scenario makes very good sense in the COVID, where doctor is very in a vulnerable position because they are meeting potential COVID patients many times a day. And if that is the case, can you develop some technology that doctor doesn't come in physical contact with the with the patient, and remotely they can still feel, they can palpate, they can press their screen, and they can still feel the patient from other end. And this way you can think of the interface via electronic skin. Yet another example is neural control of limbs. A sketch shown here, an elderly sitting, or let's say some disabled person sitting on the chair, and there is a soft robotic arm connected to the chair, which is connected to their brain. And through just by thinking, they are able to control these limbs and able to play with their grandchild. And that is a kind of improving quality of life, giving those functions which with age they lose those functions. So giving them back, as long as they live a good life. So living longer is not as important as living longer with good life. That's we can achieve with this type of technology. So these are the potential, but at the center of all these area are some scientific questions which need to be answered. And these questions are related to that. If you go and touch real world, in real world, if you try and touch objects near to you, we take touch sensing for granted, but real world comes with a variety of features, and touch sensing allows us to get those, to feel those things, to perceive those things. So these are the questions. What makes different surfaces feel differently via touch? So how my skin and brain, they work together to give me rich experience. And then when I say rich experience, mean that I may be feeling the soft part of the pen or the hard part of the pen, and through same means, which is my skin, and how my brain and skin, they work, they are in sync, and I'm feeling that they are different objects like that. So what if I lose sense of touch? Can I make artificial tools to regain lost sensory feelings, etc.? Some of these are questions I've mentioned. So these are core questions that you are the scientific question that you are trying to understand while exploring the potential applications. This brings me to the next part then. If this is the case, then let us start building the electronic skin. And first thing is, what do we do? What you need to look around, what factors need to be addressed while for the development of effective tactile skin. When I say effective, this is an important word here. I'm not talking about a benchtop that you make for lab purpose. I'm talking about a skin that can be used in real life, and for that, you have to look at various factors. As an example, there are skin can have different functionalities. It may be used to measure force, temperature, texture, etc. So there are so many parameters that you could measure based on the application. So you need to then develop skin looking at that side. If once you have selected the functionalities, next question is the mechanical or physical hardware related questions. Skin is no most of the real world objects are curvy, and if that is the case, to have a conformal contact or to conform to the curvy surfaces, skin must be conformable, flexible, stretchable, soft, compliant, etc. Those features. I'll come to the technological part later, how this is difficult to realize, and how we are adopting some new techniques to realize that. Then there are electronic factors, which is fast, reliable transaction, fast readout, because you don't want a robot to feel and then react after a long time. By that time, damage is already done. So you want a fast reaction, and for that, sensors and readout electronics or algorithms that you write, they must all be quite fast. Then there are questions related to power consumption. It must be done in such a way that you don't require much power. Zero power is ideal, but and if you can generate power, even better. I'll show you some examples. Our latest result, which was published only yesterday, where we have developed a skin which generates energy, does not consume any, only net generation. So in that regard, skin could be seen as an opportunity also. I'll come back to that later. Then after considering all these factors, you still have to look at the manufacturing. It must be manufacturable. It must be easy to maintain. Skin is also, when you talk about physical contact, skin is also the medium which faces a lot of wear and tear. And if that is there in case of robotic platform, it has implication on the cost, reliability, etc. So all these factors you must consider before talking about effective tactile skin. Then you have to look further deep into the skin. If you take a deep dive into the skin, you will see that skin is has multiple type of receptors. As you see, 4 type of receptors are shown here. So 2 are categorized as fast adapting and 2 are categorized as slow adapting receptors. They are embedded at various depths in the skin. Some are very close to dermis and epidermis layer. Then there are ridges. All these structures, they have specific function. I'm seeing some bad network quality message. Please stop me if you cannot hear or send a message, please, so that I can wait. Otherwise, I'll continue.
Participants, you have any issue? Sir, it's okay from our side.
All right, I'll continue, but in case I drop out, please you can send
I
me.
will inform you, sir.
Yeah, thanks. So in that regard, you are looking at various type of sensors which allow us to feel soft and hard the various objects and must be coming from somewhere else. So don't assume that this was from this slide. There are these type of receptors are there in a sense. If you look at from electronic hardware point of view, these are essentially sensors. Slow adapting are analogous to capacitive sensors, which give you a measure of static or quasi-static stimuli. For example, if you're holding a object, uh, and if it has to be held like this only for a long time, so this becomes a static stimuli. But if you have to move it like this, then it becomes a dynamic stimuli. So that way skin, you have to embed various type of sensors in soft layers, and interestingly the soft layer also influence the signal of the sensor. They are placed in such a way that when you press, they are able to distinguish the frequency as of the signal and various other parameters such as temperature, etc. So you have to these challenges. I'm now highlighting what are the challenges related to development of electronic skin. So you need to think about how can we integrate electronics. Your mobile phone, as an example, has electronics, but that electronics is stiff. If it was soft, then you would probably you could use it like a wristband also, but that's not there. And the key reason why we are not there is because the current technology does not allow us to bend electronics and or to embed in the soft materials. So this is a challenge. Then we are looking at the bending aspect as well. If you were to going back to the example of mobile phone, if I use current technology, then I need to redesign the robot as something having, as you see on the screen, something having flat surfaces, etc. But real world is different. Real world is curvy, and robots we are developing, humanoids, etc. As an example, they are also curvy. So you need then the new technology which can flex, we can conform to the curvy substrates. This applies in many ways to biomedical sector also, not just in my view, robotics, prosthetic is certainly a part of biomedical sector. Then you are looking at large area. So another dimension is that it is not about putting a sensor on a fingertip or putting a sensor on a joint. It's about putting sensors all over. So if you have to think, you have two eyes, two ears, they are very centralized, but skin is all distributed. So with that distribution comes a new challenge. Flexibility is one thing, distribution over large areas is another thing that comes as a challenge. And this distribution allows you to gain these rich feelings, that you are able to feel temperature, hot, distinguish between hot and cold object, or soft and hard object, or a glossy surface or a textured surface. So the feedback from large areas with all these features, what makes the electronic skin an interesting area, as well as challenging. Some of the challenges, technological challenges, etc. I have already mentioned, and other challenges are also given here. In addition to what I said, data and energy, they are also highly important. If you look at the example on the left hand side, these are various mechanoreceptors. Mechanoreceptors are the receptors in human skin which give you a sense of pressure. In addition to mechanoreceptors, you have pain related receptors, you have temperature related receptors, etc. So if you look at all these distribution, and this is not an actual distribution, these are just estimates. And from these estimates, if you just look at palm area only, you will have about 5,300 MRs or mechanoreceptors. Uh, if you would like to see detail of all the works that I'm mentioning, then I also have referred to the papers we published on various slides, and the various movies, videos that I'll be using or I have used so far. They are present on the YouTube channel of my group. If you just go to search BEST all capital underscore U of G, then you will reach all videos you can see there. So looking at going back to this slide, so data and energy, they are important. If you have to, if you want to imitate human skin, then more or less you are in a palm area. You are putting 5,000 plus sensors, which give you sense of pressure only. If you want to add temperature and other feelings, then you have to add a lot more sensors. Now, if you put so many sensors in a small area and want to read all of them at same time, then each sensor would need 2 wires. So that becomes 10,000 wires. Now try imagine if your hand has 10,000 wires, can you move your hand? It would be extremely difficult. So that comes a challenge, you have to find a trade-off between how many sensors I want to put, how many wires so that I can, without sacrificing the dexterity, I can continue robotic hand or prosthetic hand can continue to work and can give you also the feeling. Now that is the physical dimension of using electronic skin with so many wires, what physical challenge you have. But there is a challenge also, electrical challenge or challenge related to power. 5,000 sensors, they are not alone. They come with the electronics. So you read the sensor data and then you transmit the sensor data either wirelessly or through wired means. So that electronics and sensor both require energy, and for 5,000 sensors, and then think about entire body. If you were to cover entire body, it becomes electronic skin, or skin becomes a sink of power. It consumes a lot of power. One hand we talk about autonomous robot, without plugging into the mains, it can work for hours. And on the other hand, new features such as electronic skin, but these new features will drain the battery very quickly and will be a huge implication as it stands. But this is a challenge which can be easily converted into an opportunity, as I'll show later. So you have to think about these data and energy also. I spoke about energy, but the data is another aspect. So these 5,000 sensors or so, they are giving you huge amount of data, and that you need to store that data. That data is not all the time relevant. As an example, if I'm touching, if I'm holding this pen, then data coming from the point of my fingers in contact with the pen, that is important because that is the feedback I'm using to exploit. Everywhere else, it was redundant information. So there is no need to read entire skin at one time, just the skin that where change takes place or event driven, and that leads to a new dimension in the data handling, which is neuromorphic computing, etc. So only getting data from the points where there is a change. Otherwise, you can filter that out. So this is an important implication, and this leads to me to the definition of electronic skin with all these things, or conformable electronics. A flexible substrate which has various type of sensors. These can be physical sensor or a chemical sensor, integrated on same substrate with energy harvesting so that they are energy autonomous. There's a local or distributed memory so that it can handle the data, make it more computationally efficient, and signal conditioning. Any electronics associated with all these devices that you see, and communication if needed, wireless communication, but if wired is possible, then it is fine too. So with all these things integrated on the same substrate leads to an interesting direction, full of challenges but also full of excitement. These challenges are, you can imagine that electronic skin is like your computer, but this computer is now flexible, and this computer does not have a chip but has a distributed electronics because it is computing from all over. And this computer, in addition to your computer, has a camera only, but in addition to that, this computer is also able to feel your touch screen. If it is touch enabled, that is the feeling part. It doesn't really feel, it just gives you a sense of the location, but you can imagine how electronic skin can be considered as a computer that can be rolled, that can be, you can fold, etc. But it does all the functions in a distributed way. Quite exciting. So this brings me to the next part, which is the technology. What can be done? There are various ways, and I'll quickly move through this part because I'm conscious of the time. We have already spent half an hour. So looking at after these challenges, we need to look into various ways. How can we develop such an electronic skin? Of course, there is no single solution that can solve all the challenges, and there is no, in terms of time scale also, there's a lot to be done. But once you have the grand vision in place, you know the final target, you need to now find the ways. And this section is about finding those ways. So we started looking into various materials, what materials can be used. You need softness, you need, compliant substrate, etc. And then also looking at functionalities, but these softwares must also lead to some functionality. So what method can be used to process these materials to lead to the functionality? We looked into those aspects, and I'll not go into detail about those classification because that takes me towards the fabrication side, material side. I'll stick to the robotic side today. Various directions are possible. Various materials can be used to develop such a skin, and various processes can be used. Existing technology can be used, but in a modified format. So I'll talk about this. First example, as you see on the screen, is bendable systems or skin from non-bendable technology. Non-bendable technologies, the electronics that you use in your mobile phone or on your TV or your computer screens. These are non-bendable. Can we use them in such a way, in some way, that it leads to bendable system? An example is shown here. The skin that we developed for this institution called Italian Institute of Technology, that was developed using flexible printed circuit boards. So you have a robot seen here. You can see on the left hand side, which does not have any skin. Then there is a robot with skin, and then a robot next is a skin with nicely packaged skin, which is commercially available if you would like to buy that. So this large area coverage was achieved here using flexible printed circuit boards. And the coverage over different parts is also difficult because if you look at your shoulder, this point, so that's basically a spherical substrate because you have bending, two axes of bending in this direction as well as in this direction. Whereas this part, arm, etc., it is a cylindrical surface. So the bending over a cylindrical surfaces requires one axis bending, whereas bending over a spherical substrate requires two axis bending. You are dealing with technology which is non-bendable, and it then leads to challenges. How can we cover maximum area with electronic skin, which has also challenges related to bendability? So we looked into this aspect related to Fuller map, and the concept is shown here on the animation. If you consider a spherical substrate and take triangular projections, from triangular projections you can make a 2D layout of the 3D surface. Once you have a 2D layout of 3D surface, then you can split into various triangles. And this is the fundamental basis of triangulation technique that we use for 3D imaging. Those who are familiar with computer graphics, they would understand what triangulation technique and 3D imaging are. So that knowledge is then now brought into hardware and brought into development of electronic skin. So once you got these triangles, try to place the patches, triangular patches. This is the reason why you saw triangular patches on the skin on previous slide. Once you have covered, then you rebuild the whole from 2D, you rebuild 3D surface again. And if you do that, then it leads to a generic approach whereby you can cover any robot, any type of shape with the electronic skin. And here is an example. This is iCub, as you saw earlier. These are examples of skin. This is, as you can see, this is flexible. It is developed on flexible printed circuit board. Each triangle has 12 sensors. These are all capacitive sensors, and they are integrated on various shapes. You can see the bending at this point, or a cylindrical body part here. This is on the palm. This is the top side of the skin patch. And you see these electrodes. Basically, these electrodes serve as the bottom electrode of a capacitive sensor. If you look at a parallel plate capacitor, when they come closer to each other, as you see here in this figure, when this is the normal capacitor, when they come closer, the capacitance would change because it is epsilon area divided by thickness. So if thickness distance between two electrodes is changing, you will have a change in the capacitance, which is then read by the electronics sitting on the back side of the triangle, as you see here. Now this is the same chip that we use in our mobile phone. This is a capacitance to digital converter chip. So there are 12 capacitive points. You convert directly into digital value and integrate it on the back side, and they are then routed. These joints that you see here, the triangles are connected. Wires are going through these points. So you can then get data from various sensors, and for each skin patch which made 16 such triangle, the data is sent to a microcontroller. From microcontroller, once you get the data from a patch, you send it to the computer processing unit, CPU, or the brain of the computer, and that is communication. In this case, was through I2C channel, I2C communication protocol. So this way you can use then skin from different parts of the body. And some examples are shown here, how the skin, which I mentioned is a general skin, how you can have the skin on various type of robots. So iCub is shown here. Then there is, this is a Casper robot, which is used to teach autistic children. Then there is, now this is SoftBank Now robot, which is shown here. It is commercially available. This is shrunk robotic arm, which is in automation sector. They use this kind of robotic arm to highlight some example versatility of this approach, that you can use this to cover robotic hand in various places or various type of robots. Scientifically and in terms of interaction, this leads to interesting direction where you can think of a robot using tactile feelings as well as vision. There's a lot of work already done on vision, but not much there in the touch. But as humans do, a coordination between vision and touch. And this touch is not a single point touch. Now you are looking at area contact, so you can press. So that kind of coordination leads to interesting directions in terms of advancing robotics research or studies related to robotics. Getting multi-sensory feedback, sensory fusion. So how could you operate if you have to see an object as well as feel and then plan? As we do, we use all sensory modalities. We use vision, audio, feeling, smell all together, and to execute daily so many tasks. We don't really separate them out. And if that is the case, and humanoid are a way, one direction that we have chosen, not just humanoid shape, it can be any other shape also, but touch and vision, they could still be, the coordination is still needed. And you can see on the screen how various contact points, you can see these areas, now this area, they are mapped. So this led to an interesting new approach in the robotics. Before the skin was available, people were talking about picking and place, putting some sensors on the fingertips, etc., and then doing tasks such as pick an object and place elsewhere. Forgetting the fact that our skin is distributed and we do so many tasks on daily basis where we don't use fingers. As an example, if you want to lift a sandbag and you want to just grab it and then want to pick and place at other, from point A to point B, you don't use your fingers. Instead, you just grab, and it is the large contact with the body parts, which you feedback from those body parts you rely on and to execute this task. So this research then led to advances in the new paradigm in robotics research, opened a new field whereby large area skin or large area contacts were exploited to execute tasks. That task could be particularly in constrained environments such as tunnel, where you cannot move. You need feedback from all over body. So those are some of the examples. Colleagues in IIT, they went on to miniaturize this skin and integrated it on the fingertip also. Uh, and as you can see, then they were able to manipulate soft object as well. This technology can also be used in many other areas, not just robotics, but also could be used for rehabilitation or even for fashion, etc. If you want to extend further for in terms of commercial domain. Examples are shown here. For example, you can, like embroidery, you can integrate on clothing. And once you do that, this color could be matched with the walking pattern. And that's what I mean by in the rehabilitation, etc. So you could integrate and connect, use electronics in many ways. Or you could also connect, as I was mentioning, through in a fashion concept. You may have seen already some textile, which LEDs, etc., already integrated on the substrate, flexible substrates. But all these technology also have challenges and problems, and one major problem is that when you use flexible printed circuit boards, you don't really get an ultra flexible or ultra conformable thing. I cannot integrate or wrap that skin around my fingertips because there's a certain degree of bending. It does not go beyond that. If I try to bend it more than that, first the chip on the backside, the soldering will come off. So the chip will come off from the substrate, so I cannot use it. If I try to further bend it, the electrodes that are sitting on top, because electrodes are made of metal, that will also break. So there is a physical limit of bending. I cannot have a ultra bending, but what it does is it gives me some handle at this point, because there is nothing that exists. It gives me some way, some tool to advance the science, advance the research. This brings me to the next part, where some of the technologies that we are exploring and several other groups are also exploring, in terms of how could we make electronics more flexible, and at the same time, we should not be compromising the performance. If my computer is fast, then it should be remain at least same level of performance, and I should also be able to roll it. So I should be able to roll it like a calendar, etc., and carry easily. So for that you need electronics, ultra flexible electronics, and what we are doing in this direction is the silicon, which is the main material used for as a substrate for or electronic material used for development of electronics. But silicon is a brittle material. You try to bend it, it will crack quickly. So we are overcoming those challenges, and we have developed ultra flexible silicon chips. And simple technique we use for this is that if you imagine an aluminum bar, thin it down into slices, what you get is the aluminum foil, which you do use every day for food packaging. It is a similar technique that we are using here. You got a wafer which is about 500 micrometer thick. It is stiff. You thin it down to about 15 micrometer. And when you thin down to 15 micrometer, it becomes flexible. And that flexibility, as you can see, it does not crack. Of course, if you press it hard, you will see the cracks, but that way you can achieve the bendability. And compact electronics can also be integrated. You can have, for example, a microprocessor which is flexible, and you can put it on the skin. There will be other dimensions also, which for example, microprocessor also generates heat, so you cannot put it on the human skin directly without considering the heat aspect. But on a robotic platform, you could do that. So this then leads to another point. This technology is good. It gives you a compact electronics, could give you flexibility, also high performance, but it does not go to the large area. Skin is also large area. You have to actually look at all these technologies that I'm presenting. You have to look them together. There is no single technology which solves all problem when it comes to electronic skin. It is not like a CMOS camera or a CMOS imager that you got and you have in your camera and you are using all visual techniques. There's no unique solution currently available for touch sensing. So when it comes to large area, then we go back to the printing. Interesting new dimension not only for the field of robotics, but also for the field of electronics. Currently, we develop electronics in a highly specialized instruments located in one place. But if you can develop techniques such as printing of electronics directly, then at some point think about printing from home as you print papers today. So they're in that direction the techniques are, and this is a long-term solution. This is not something that you just exist and start using. So it will take time to get this technology to have a mature version of this technology. So what we do here is we transfer print, we pick up nanowires from the wafers and transfer them on flexible substrates, leading to this flexible substrate is also an electronic substrate, which can then be used to develop the electronics and sensors, etc. Some examples of these approaches are given here. I'll not go into detail of the approach itself. If you want to have detail, maybe you could go to our website. Most of our paper are open access, so you will be able to download our papers. So this can then be integrated on various flexible substrate or a tattoo-like skin that you see here, or some other examples that are shown here. The key idea here is that you are picking wires from wafer. This surface is limited. This is what you get commercially. But by putting this way and transferring on a other substrate, you can think of printing on a very large area. So that large area could be about 1.5 meters square as the human skin, adult human skin, or it can be other areas also as needed. That way you can develop, you can transfer at desired locations also, not everywhere. If you don't want it this corner, then you don't have to transfer. So you can be very selective. And this leads to interesting dimensions, potentially having potential to trigger transformations in electronics from very centralized fabrication facilities to decentralized electronics where people have control over the hardware also, not just the software. So some example in this regard is given here, and I'll not go because this is going towards electronic devices, which is not the focus of today's talk. But we work in these areas, and these are our own examples. So you can see how we are able to connect to different areas also. So this example, you see this figure, this is all the electronics, ultra flexible electronics, using the approach that was presented in previous slide, integrated on various substrates, as you can see here. And we have tested them, and in terms of performance, the performance is at par with current electronics. Going forward, there may be further possibilities. Instead of transferring, kind of picking and placing, stamping, you may also consider the same scheme, but in a roll-to-roll fashion, like you print newspaper as a roll, you may consider printing electronics like a roll. And I have explained these techniques in this proceedings of IEEE paper that was published last year. This slide shows some example of these printing, how you could print nanowires and then print them and use them to develop electronics. Following then, we use this technique to get electronic skin, where you have nanowires printed on the substrate. As you see here, these are nanowires. They are integrated with the sensors. So this is a pressure sensitive layer. You press it, the resistance will change. When resistance changes, this resistance changes. This is a transistor. The current between source and drain will change because of this. So this leads to modulation of channel current, and that is then picked up by the electronics, which is all printed here. So this is just the sixth scheme that we have for printed electronics. Not only this, we are then looking into other aspects such as how can we integrate. I mean, skin, if you look, is interesting because it has muscles, it has sensors, all integrated and in the same soft material. It's kind of seamlessly integrated, coupled sensors, actuation, computing. And then you have to think about similar structures going beyond just putting at the outer surface. Can we embed all these sensors inside the soft material? One example I have is here. So this is if you look at this is the basically intrinsic sensing over the body is used for the movements. Like that, we have just developed this. This is still in review. This work where we have sensors. This material itself is a sensor. You consider that way. It's uniformly distributed. There is no distinct sensing element here. It's uniformly distributed, and these are wires, conductive wires. So we control them, and you can move these soft objects. Other dimension is that you can embed electronics directly into 3D printed surfaces. So one example is here. So you print 3D printing is an interesting new technological advance that we have been seeing over the last couple of years. But the 3D printing that you normally see is all about printing plastics and giving shape, 3D shape to that plastic. One new dimension that we have added in this area, that when you print, you design in such a way that it can also become, the structure itself can become a sensor. As you see, in this case, this hand was printed in such a way that you start printing the plastic, then you print metal. So multi-material printing is one aspect. You are able to do the both. Then you leave a gap that you see here is a gap, and then you add one more electrode and then plastic, and then you start printing. In the process, you have actually printed capacitor into the structure itself. So you try to press, as you see here. So you press the thumb, you get the signal. You press the next finger, you get the response. So this is all capacitive sensor in the structure itself. That way you can make smart structure, intelligent structures, robust structure with sensing modality. Some examples for which were given in mentioned in previous lecture about prosthetics. If you could redesign and develop those prosthetics with this type of sensing and embedded in this structure, it will be a low-cost approach as well as robust with additional features. So this is another dimension that we are currently exploring. Then there is something related to computing. I mentioned that computing is another challenge that we have in electronic skin. And neuromorphic computing is one way, or you could develop strategies so that at the point of contact itself, you get multiple information. As you see here, this is a 6x6 capacitive touch sensing array integrated on the robotic or 3D printed hand. There is an algorithm written. So the signal from the sensors is picked and fed into the algorithm that you see here. And this is now we are working on the hardware implementation. And it can give you point of contact as well as direction. And as well as third aspect is related to it can give you the amount of force that you are applying. And this processing is all done in a way as a neuron would do. And this way you can have very efficient computing. You will have efficient computing would require less power, and that would solve questions, some of the challenges related to energy and data. I mentioned about the energy new aspect related to skin, and I think in the interest of time, I'll just cover this last aspect and I'll stop that. I will skip the third section, which is how are we using these technologies to, or maybe I can pick up one or two examples just to give you a flavor. In terms of energy, I mentioned that all these sensors, they require a lot of energy, and you need currently solutions are I can use lithium-ion battery, or we can directly supply, but they all add to the weight also. And in that sense, skin gives you functionality, but that's it, nothing more than that. Skin is a large area which comes in is exposed to the ambient. So why not we use this large area to generate energy? And that leads to another new direction within the field of electronic skin, flexible electronics, robotics, etc. So we started working in this area. We compared how can we generate energy. There are so many solutions. People talk about generating energy by walking pattern, piezoelectric, pyroelectric, thermoelectric, triboelectric, all those areas are there. But none of these areas, none of these approaches lead to level of amount of energy that would be needed or sufficient for electronic skin, or to power so many large number of sensors. Only solution that we came closer to that was to the requirement was the solar cells. But the solar cells, number one, they are not flexible. Number two, if I use solar cell in context with electronic skin, it must be covered with a touch sensitive layer, because touch sensor is the topmost layer. If you do that, most of the solutions you come in literature, they block the light. So if light is not reaching solar cell, it will not generate energy. And this is also an important concept which I'll come later that you can exploit. So the first thing for us was to develop something that is touch sensitive, that is transparent also, and we looked into graphene. Graphene is transparent, touch sensitive, and we then transferred it into large area. There were challenges related to transfer over large area, but that's a subject related to fabrication, probably a topic for some other talk. Using this graphene on transparent substrate, we developed we followed this process that you see here, fabrication process. We obtained capacitive sensors compared with the similar sensor with the traditional metal that are used in fabrication. For example, gold here, the blue color, and red color is the graphene. So it led to significant improvement in terms of sensing the sensitivity of response, and it was transparent. It allowed light to pass through. As a result, we integrated this skin on top of solar cell, as you can see examples here. So this becomes a solar cell which is generating energy, and it is also touch sensitive. You could take it that way. Graphene is 98% transparent, more or less, and that 98% transparency means it was not blocking section of light. It was still leading to generation of same amount of power. The skin being made of graphene, graphene is highly conductive, does not require that much power. So it was like 20 nanowatt per meter, nanowatt per centimeter square. That was the kind of energy we needed. And this led to the next thing, that you are generating energy more than you need. 20 nanowatt is a very small energy. So if you are generating more energy, then you can also add to the skin energy devices, energy storage device. I'm not talking about battery, I'm talking about some flexible batteries or flexible supercapacitors, and we have done that also. This example in this video shows the Tactile, the skin, graphene-based skin integrated on a prosthetic hand. The first video was when the tactile feedback was disabled. Now tactile feedback is enabled, and you can see the difference. With tactile feedback, grasping of soft object is dramatically improved. And that is this is the another example. I mentioned that you have the solar cells here. Under solar cells, we integrated supercapacitors, flexible supercapacitors. So solar cells are generating, are charging the supercapacitors inside, and the energy from supercapacitor is then used to operate some of these motors. Now these movements at this stage are not great, but this is the first step towards developing using skin as a source of energy. In this case, you still have sensors which need energy. There are techniques where you don't need sensors, still you can get touch sensing. I'll come to that just now. This is another example that you see where we generate energy using triboelectric means. So we have a very thin sample here. If you just tap it like that, then you can see that you can generate sufficient energy. So we are also exploiting this part, not just for robotics, but also capturing energy from sea waves. And that is another subject, topic of another talk. So these are ways to generate energy. From energy autonomous skin, we are now moving towards net energy generating skin. A skin that does not have touch sensor, yet provide touch sensing, and does not, and only provide energy, generates energy. This is one example where we have used solar cell in that sense. So you can see solar skin. There are small solar cells. These are all commercial, integrated on a very soft material, PDMS, as you can see here. If you put them on the palm area, then simple concept is that if you cover the solar cell, it will not generate energy. That means when solar cell is not generating energy, there is a contact. So you don't need a touch sensor to detect that. Solar cell property generating energy or not is used to find out whether it is a touch or not. Likewise, when something is approaching, based on the shadow, based on the shadow itself, you know what is approaching, and you can find the proximity also, because energy level will reduce. From energy level, you can map it to the distance, and that way you can use the skin also for proximity sensing. We have developed this skin recently. As I said, this is a open access paper published yesterday only in IEEE Transactions on Robotics. There are some videos that I'll show. Some videos are present on my group's channel also. So this is an energy generating electronic skin with intrinsic touch sensing. All electronics is embedded. This is integrated on a 3D printed hand. And the key aspects are given here. Actuation module, there is a sensing module which gives you shadow and proximity sensing, and then there's a power module here that we see here. So these are three main modules for the solar skin. It is distributed array of miniaturized photovoltaic solar cells and IR LEDs, infrared LEDs, integrated on soft and flexible substrate. Solar cells, they are basically in this case energy harvesters and sensors together, simultaneous operation. This is important also for skin, because more layers you add, more sensor you add, you more weighty it becomes. And if you have a distributed, if you put a lot of weight, moving hand itself would be difficult. So using one device for multiple functionality also helps in that context. So solar cells use as energy harvesters and sensors at the same time. Sensing parameters in this case are contact location, object shape, edge recognition, proximity detection, etc. And in terms of energy generation from the palm area alone, we noted that it can generate net 380 milliwatt. And this net means after considering the power needed by electronics. So it is generating, part of this is taken by electronics, and net what comes out is 380 milliwatt. If you assume such a skin to be over the entire human body, which is about 1.5 meters square, then we'll be generating, you can multiply this from palm area, you can scale it to body, you will be generating more than 100 watts. Now that's a lot of energy. And if that kind of skin goes to, for example, a rover which is going to Mars where there is no power supply, you can imagine the implication or impact or positive gains with that. This is really opening a new direction how electronic skin could be used in a new way. So this is the generated two. There are two sensing modes, shadow sensing and proximity sensing. At this point, we have already got new modes which are not published yet and will be publishing in due course. This is the details about electronics behind it, so I'll skip that part. What it does, as you can see, when an object approaches, etc., you can detect that, but probably the videos will show you better. So if you look at, this is the solar skin operating in a shadow mode. So that's the solar skin here. This one is the solar skin here, and this is what you see on the screen, on the computer screen. So you take your hand on top, you move your hand, you can see the responses here, and these are simply because there's a shadow, and the amount of light solar cell is receiving is varying because of these movements, and we just capture those things. So that leads to a new direction. Here's another example where robotic hand is integrated with solar skin. So you can see this now, the skin is on the robotic hand, object is approaching. When object approaches, you can see all the color changing from different directions. So it is able to detect. This also opens a new direction in a sense that most of the skin, they act after the contact has been made, but this skin will allow us to act before contact is made, and then that would, interestingly, would lead to new ways of manipulating objects. So this is an example of proximity sensing. So you have the sensors. Solar skin also has proximity sensor, because you may have a question that in the dark there is, how do you generate, or how do you distinguish there is something so approaching or not. So for that, IR LED, infrared LEDs, they work in the dark also. That also has been integrated on the skin, and you can see the response directly here. This is an example where robotic hand with solar skin is grasping an object while it is approaching. So you can see based on the solar cell data, the hands move and they grasp the object. The response is also shown on the right hand side from various solar cells. This is example how you could use it for human robot interaction. You can see solar cells, when somebody approaches, based on the feedback, robot is able to move back, and that leads to safe interaction. Some example that I highlighted in the beginning, that robot should be able to stop or should be able to move back when a person approaches. So this is an interesting example where skin is generating energy. Part of this energy could be used to move the robot itself, and also leads to safe human robot interaction. I think I'll skip rest of this part. We are working a lot in terms of, for example, using sweat-based energy devices, developing rehabilitation strategies for deaf, blind people, remote control. Also, we have developed various pressure sensors and temperature sensors and integrated them on American. We have demonstrated that possibly this could also be a solution for with the current challenges in terms of COVID, that you can connect these the temperature and strain sensors on wearables, and in that sense you can get directly information about temperature and the chest expansion, respiratory volumetric expansion on the mobile phone. From mobile phone you can interpret this data, and you can identify hotspots of COVID, and you can take appropriate action, as needed. So we have also been using this technology to solve some of the current societal challenges. We also use our 3D printed approach, as mentioned earlier, to develop a DIY ventilator, which again is published. Details are published in this paper, Global Challenges. It was published earlier this year. You can This design is open access. You can design your own if you want. The details are also available on my group's website, and that's what you see how it works. So this is all. You can even operate this ventilator by hand. So in case in remote areas, if you do not see power, then you can also and those vision how you can do it, they are explained in our paper. So I'll skip. There are several other examples that I have, but to conclude, I'll say that tactile sensing is an important area. It is important for safe human robot machine. Flexible electronics or conformable electronics, which is used as a vehicle to achieve tactile sensing, is a disruptive area on its own that adds new dimension to electronics industry, and enormous impact in consumer electronics, aviation, space electronics, robotics, life science, lighting, military applications also, and sustainability, because electronics manufacturing currently uses unsustainable practices, so it is eco-friendly in many ways. Electronics manufacturing by printing is a promising, cost-effective approach. Part of the long-term solution by printed electronics is what I presented. I think that's if we can achieve that, that would be quite promising, cost-effective, and sustainable route for high-performance electronics in the future. And electronic skin technology, as such, if you look, it is a technological platform. Then it can underpin advances in several applications, which include bionics, healthcare, Internet of Things, wearable systems, and also smart cities, etc. Well, with this, I would like to acknowledge the funding that I have been receiving from Engineering and Physical Sciences Research Council, European Commission, Scottish Funding Council, Royal Society and Royal Academy of Engineering, as well as my group members. If you want to go in details of what we do, then my website is here. My email ID is given. My Twitter handle is given. There's a TED Talk which summarizes what I've said. It's just 10-15 minutes animating the inanimate world. If you look for that on YouTube, you'll find the TED Talk. My group's TED YouTube channel is here. You can find all the videos that I presented today. You can, on some description, you can find all these information on the websites. Thank you very much.
Participants, if you have any questions, you can ask. Otherwise, we will close this session. Thank you so much, Professor Dahiya, for such an enlightening and exciting talk. Hope all the participants must have enjoyed this session, and we have learned a lot during this session. And sir, your group is doing really a challenging work in this area. Thank you
Well,
so much, sir, for giving us your valuable time in spite of your busy schedule. Thank you.